Hi guys, welcome back. It's been a while since we've done a video. We're starting fresh from quarter 2 here. This is forces. Okay, what is a force? I'm going to throw up a lot of these things and I'm going to text these things in here, so maybe I'll just leave them right here and be like that. So when an object interacts with another object externally, we can describe that interaction using a force. Now it's a little bit gobbledygook here in here. At this point we will get into internal and external forces. We're talking big stuff. So even though a clock has like winding gears and a hand that ticks, and there's a lot of forces and torques and things going on inside of a clock. But if I took that clock and I chucked it, that's the force that we're talking about. I applied a force to that clock and I threw it, and it accelerated away from my hand, and then eventually it's going to fall into the ground, so there's another force pulling it down, right? So that's the kind of things we're talking about here. A force is a push or a pull. Anything that is going to put pressure on an object to change its movement. And I say change its movement because you don't necessarily need a force for movement to happen. You need a force for acceleration to happen. For something to go from rest to some velocity, to go from some velocity to rest, or if it already has a velocity, to change its velocity or change its direction or cause a turn, right? Those three types of accelerations we've talked about. So if you see an acceleration, you know you have a force causing that thing to move. And we'll get into Newton's laws a little bit later. Right now we're going to go through the types of forces. So there's two types of forces. We'll cover this one, field forces. There's not that many of them. There is the force of gravity, so force subscript little g. This is the gravitational force. That is caused by masses pulling on each other. It seems a little bit absurd, but you are attracted to the chair you're sitting in, and the chair you're sitting in is attracted to you because both of you have mass. Okay. Now there is some modern physics discussions about what actually causes this gravitational force, and maybe it's not actually mass, but rather the shape of the space-time around that mass. For our purposes in this class, it's the mass. Okay, all objects have mass because they have matter. All matter has mass, and all matter is attracted to all other matter because they all have mass. That's that. Okay, primarily we're talking about Earth's force of gravity, which causes an acceleration of 9.8 meters per second squared, which is not the force, that's the acceleration. Another field force that we will talk about later on is the electric force. This is not quite the same as the electromagnetic spectrum, but it's a piece of it. This is the electric part of the electromagnetic spectrum. There's also a reciprocal magnetic force that when combined you get the electromagnetic force, and we can go into that later on when we talk about that in like distant chapters, probably quarter 4. But understand that both the electric force and the gravitational force are what's called field forces. These are invisible forces. The electric force can pull and push. The gravitational force is only a pull. So electric force, positive, there would be a push force, whereas a positive negative would be an attractive force. Okay. So contact forces, these are much more common, much more tangible things to deal with. We have the force due to tension. Strings, these are pulls. Pulls only. You can pull the string, pull the rod, tension force in your finger. Things that you're pulling on have tension force. The normal force is a little bit odd. This is a push only, and it's perpendicular to or just from a surface. So a table pushing up on a book, the ground pushing up on your feet, or that chair pushing up on your butt are all normal forces. The spring force. Now this is going to get a little bit sticky. This is also could be considered the static friction force. In this case, we're going to say, until we start differentiating, we're going to call this the spring force. This can be a push or a pull depending on how the spring is made. A leaf spring in a truck, right, where the axle and the truck bed here, that is a spring. That leaf spring, that would be a push. A spring scale, which starts out, you know, the little fish scale, it's all compressed, and then you put something on that and it stretches out and it wants to come back together. That could be a pull force, but that is the spring force. And it kind of depends on the spring. Each spring force has its own coefficient to go with it, depending on the steel and the rebound effects, or how hard it is to push or pull on that spring. Friction, of course. This could be anything from like drag on a boat, or air drag, or air resistance, to rubbing your fingers together, to your tires on the road, shoes on the pavement, all that sort of thing. So friction. Friction can be a good or a bad force. It is opposite of the motion. And it's based on, it's a physical property based on the microscopic edges of materials. So there's a coefficient of friction that we'll talk about later, just like the spring force has its own spring constant based on the spring. Well, the frictional coefficient is different between any two different materials. There are known friction coefficients, and we'll actually solve for a couple of those in the lab. So we have two types of forces: contact forces and field forces. Drawing forces. Okay, this is really, really important. We depict objects with a center of mass. Okay, so if I had a box sitting on a table here, I am concerned about the center of mass of that box. And so when we draw forces, all forces, let's say I have a box sitting on a table. That box is being pulled to the earth by a force called gravity. Now, the box is not accelerating towards the center of the earth, so I know there must be something pushing against the box, and that would be the normal force of the table pushing up against the box. So I know the box isn't floating away because it has a downward force, and I know the box isn't going to the center of the earth because it has an upward force. These forces tend to balance each other, where the normal force and the force of gravity are equal to each other. If the force of gravity was greater than the normal force, you would see an acceleration downward. And vice versa. If the normal force was greater than the force of gravity, you would see an acceleration upward. This thing would like levitate, okay? Which we can do with magnets and all kinds of other things, right? If I push on the box, okay, so I'm going to come over here, I'm going to push the box that way. I have to draw my force coming out. So I wouldn't draw it going in, I'm going to draw it coming out. And it's an applied force. Now, applied force, I didn't write that down in your list of forces. It's kind of like a catch-all. It's just, you can just stick this applied force anytime something happens. I mean, you really could call all of these an applied force, right? Typically, we reserve applied force for actions that we do, or something that a machine does, or something like that. So this is the applied force. Now, because the box is now moving, we have what's called friction. So friction was opposite of the direction of motion. And so what we've done is we've drawn a vector diagram, more specifically a force vector diagram, just like the other force vector diagrams that we've done with kinematics, talking about relative motion and this and that, and vector A going in this direction and vector B going in this direction. And you can add those up and find the components and all that stuff. All that same stuff applies to force vector diagrams, often called a free body diagram. You may see it written either way. So a free body diagram or a force vector diagram is probably the more technical way to call it, but everybody calls it free body diagram. So we will probably use those two terms interchangeably. Okay, so when you draw this, you don't need to draw all the extra stuff. Okay, it can be helpful when trying to understand a problem as you get going, but eventually you're going to want to get to this point right here. So let's go through a few examples. Object in free fall. I've got a ball right here. I just dropped it off a cliff. What forces are acting on it? Just gravity. Object in free fall has one force acting on it. How about a baseball? Now, a baseball that has just been hit by a bat has the force of gravity and the applied force of the bat at some angle from the horizon. Okay? Now, as soon as that baseball comes off the bat's no longer affecting the baseball, and so it becomes an object in free fall. Just like the cannon we were working with when we did projectile motion. If I shot a ball down the hallway, as soon as that ball left the plunger was no longer applying a force to it, and gravity was the only thing pulling it down. Let's bring some hills in here. This is a car parked on a hill, also climbing a hill. It's the same free body diagram, the forces are just bigger. Now, which direction does gravity pull? The force of gravity pulls straight down. It doesn't really matter what it's sitting on. Force of gravity is straight down. The normal force is perpendicular to the surface pushing on it. In this case, it's the road. And so perpendicular to the road, right, 90-degree angle here, perpendicular to the road is the normal force, pushing the car up away from the road. Now, it's parked on the hill or it's climbing a hill. So why does this object not get pulled down? If we tease this out a little bit, I know that this is a force vector diagram, and forces have components. So a piece of this gravity is actually pulling the car downhill. Our car's parked. So why is gravity not pulling it down the hill? Well, there must be friction between the wheels and the pavement. Force of friction. What if you were sledding down a hill? Right? Well, it's actually the same thing. There's nobody pushing you down the hill. The reason you're going down the hill is because of this X component of the force of gravity. Some of this gravity is in the X and some of this gravity is in the Y. The friction on a sled hill, you're working on snow and ice, it's really, really small, right? What happens if I had bald tires? I would be sliding down the hill with my bald tires, right? Or the parking brake went out and all of a sudden the friction of my tires aren't holding, and so I would slide down the hill. Okay, so objects on an inclined plane are going to have force of gravity straight down regardless of the angle. This is the angle of inclination here. And then your force normal, perpendicular to the surface on which you're talking about. And then force of friction is going to go uphill. Okay? And we can get into something more complicated. Let's say you're mowing your lawn. A lot going on here, right? you have your lawnmower sitting on your grass, and you have the force of gravity. You have the ground pushing up on it, and you are mowing the lawn. How do you mow your lawn? Well, you push down on your lawnmower, right? You have this thing, so you are actually pushing down a little bit on your lawnmower, and so you have some angle down. This is an applied force, but the lawnmower is not actually going through the earth. The lawnmower, the center of mass of the lawnmower, is actually going horizontally in that direction, because that's kind of where you're pushing. So you've got the force of friction opposite of the motion. So if you're mowing your lawn, this would be the free body diagram that you're setting up. Now I want to go back to this scenario right here, or this scenario, and I'll talk to how you deal with these angled components. You have to pick your axes. Now we understand that the typical XY grid coordinate system is arbitrary. We've chosen that, and usually Y is straight up and down and X is the horizon. It doesn't have to be that way all the time. So if I switched my axes so that this becomes my X and this becomes my Y, right? If you kind of like orient yourself a little bit here, then I can handle a lot of these angles a little bit better. So if you really wanted to, you could redraw this. You could have the normal force up, you had force friction this way, and then you had this guy here, gravity, right? Now I don't like to redraw because, well, one, it's more work, and two, I feel weird that gravity is off to the side. You can do that. That's really what we're going to do here. And I've got my X and my Y. You can kind of look at that for comparison. These are the same pictures. I'm going to stick over here because this is how I like to work. If you feel more comfortable over here, you can do it that way. I'm going to go ahead and get this out of my way though. And what we're going to do is we're going to find the X component of gravity and the Y component of gravity. So I've got the FGX and the FGY, which were the composite vectors of my full vector here. Now that forms a right triangle. And we got like a little bit weird thing going on here, okay? So we've got this leg, this angle, right? This is the hill, and let's say this hill is just to make it easy, is 30 degrees, right? That's a right angle. Now recall that the triangle principles, or the shape principles, all three, or if you were doing a square, all of the angles have to add up to 180. So because it's a 90 degree angle, I've already got 90 and minus 30. I can then solve for this angle up here, which is my common angle that I'm going to need to work with my vectors here. And so when I do the math, 180 minus 90 is 90, minus 30 is 60. Okay, so my complementary angle here, or whatever you call that, is 60 degrees. Okay, that's important because of my other triangle, right? This one here, this one was the F of G, the F of G of X, and then this is F of G of Y, and I make a different right triangle. So you got to kind of like shift gears, and they share this angle. Okay, now it's important for you to take your hill angle and put it into your force vector angle. Okay, if that makes sense. And of course I've got my F of N and my F of F up here to deal with later. Okay, so keep that in mind. We're going to come back to this. In general, your force vector, just like the other vector angle math that we had to deal with, I can't deal with this f of g at an angle, I can't add these up and try and cancel these. I can't deal with that because it has both x and y components built into it, and I can't see them or I can't get at them. So I have to break these up into its components just like normal, and then I can handle the component forces when I do my addition and subtraction. Okay? Newton's second law of motion. The net force for external is directly proportional to mass times acceleration. So what that means is that a net force in a certain direction causes acceleration in that direction. A magnitude of acceleration caused by a net force depends upon the object's internal mass. If an object has more mass, it has more inertia, therefore less acceleration. Let's see what they're talking about here. If I divide the mass over so that I have the mass and the acceleration on different sides of the equality, this is saying the net external force divided by the mass is directly proportional to the acceleration. So if I increased the mass, then the acceleration would go down. They're inversely proportional to each other. Only external forces exerted on an object affect that object's acceleration. So if I were to increase or decrease my acceleration, what I would have to do, assuming that my mass stays the same, I have to change my force, my net force. Okay, this little piece right here is really, really important. If my net force goes up, then my acceleration goes up, or it changes. It could turn, right? So net force. A net force is equal to all of the forces added together. Keeping in mind the law of independence of dimension, the net force is equal to the square root of the net forces in the x dimension squared plus the net forces in the y dimension squared. Okay, so all the same vector math that we've been doing with kinematics and the relativistic position and velocities and all that, same thing applies. Okay, Newton's law refers to the net motion, right? Most people could recite back F equals ma, right? It was a little bit more complicated than F equals ma. It's the net F equals mass times acceleration. And so we understand that a net force is the addition of all of the forces acting on that object of the same mass, right? The same object, all the forces acting on one object brought back together. And we saw earlier with the different triangles and the force of gravity on an object sitting on an inclined plane that you have to break out the component vectors of the full vector. And so once you find your net forces in the x and you find your net forces in the y, then you can without a doubt say what is your net force, your big capital force, right? All right, so let's go through a couple examples.